Welcome to the materials for the fourth session in this mass spectrometry course, and in this lecture we're going to start looking at quadrupoles and ion traps. In the previous lecture we covered a basic introduction to the time of flight mass analyzer. In this lecture, and the following two, we're going to introduce quadrupoles and ion traps and related types of system. Quadrupoles account for the largest share of mass spectrometer components in the world. These are the workhorse mass analyzers in most GCMS and LCMS systems. And even in the more advanced mass spectrometers, people usually focus on the top-end mass analyzer and often forget that there may be many quadrupoles operating inside as well. So take for example this Orbitrap system from Thermo. Up here is the Orbitrap mass analyzer. But before an ion ever reaches there, it can have passed through 9 other quadrupole or related elements on the way. So it's important to learn how quadrupoles work for the instruments where they're the only mass analyzer, but even in hybrid mass specs with multiple mass analyzers inside them, the effect that the quadrupole has on the ion beam may be apparent even in the high-end data. So let's start at the beginning. What is a quadrupole? Well, a quadrupole is a saddle-shaped electric field. Imagine a rubber sheet that's been pulled up on two sides and pulled down on the others. Here you can see what that shape looks like in both 2D and 3D. When we need to make a quadrupole electric field in a mass analyzer, we use 4 electrodes, and ideally these should have a special hyperbolic shape. The quadrupole potential field is generated right in the middle. Now this shape is only 2-dimensional, so obviously we've got to turn it into something 3-dimensional if we can make it and turn it into a mass analyzer. And the way we make 3-dimensional shapes from 2-dimensional shapes is by applying some kind of symmetry to them. So if we take our 2-dimensional quadrupole shape and rotate it around this axis, then we make something called a 3D or Pol ion trap. In this form, this blue electrode rotates round and connects to the other blue electrode to form the single ring electrode in an ion trap, whereas the 2 red electrodes spin round upon themselves to make the end caps. If we change the location of the axis, then we generate a different kind of ion trap. If we put the axis over to the right-hand side here, then we make something called a toroidal ion trap. This electrode is spun round to create the central spindle, whereas this electrode alone describes the ring electrode. These 2 red electrodes form the 2 end caps. Only now, instead of simple cones, you can see that these end caps have W-shaped cross-sections. This type of ion trap is only made by a single manufacturer, and it's not commonly used for applications in the biomedical or pharmaceutical research areas, so it's quite possible that you'll never come across this in your professional lives. Lastly, if we take this 2-dimensional shape and translate it along an axis, we can describe what are by now the 2 most common types of quadrupole-based mass analyzer. In these designs we have 4 separate electrodes arranged in a square formation. And the quadrupole mass filter is the best place to start looking at how quadrupoles work and how you can turn them into mass analyzers. To make a perfect quadrupolar field, you need to use hyperbolic electrodes, and these electrodes need to extend to infinity in all directions. Of course, we can't make infinitely big electrodes, and hyperbolic shapes can be expensive to machine, so in some commercial mass spectrometers you'll find they use different electrode shapes. Often cylindrical rods are used instead of hyperbolic electrodes. And these do work in mass spectrometers, but the fields they produce are not quite as good as you'd get if you had perfect hyperbolic rods. Here you can see the end-on view of one of these cylindrically rodded quadrupoles. In use, a quadrupole like this has 2 main modes of operation. There's the mass selective or mass filter mode, and the ion guide or RF only mode. Let's imagine we have an ion beam coming from this end of the quadrupole that contains ions of many different mass to charge ratios. If we put the right voltages on the quadrupole rods, we can set them up so only ions of one mass-to-charge ratio will be able to make it out the other end of the quadrupole. All the other ions will go unstable as they pass along the length of the quadrupole and will hit the rods. And it's worth looking specifically at the meaning of unstable in this context. This doesn't mean that the ion becomes unstable and breaks apart. It means that the ion's trajectory becomes unstable, and so its amplitude increases until it hits one of the rods. And we'll look at this in more detail later. If we set the same quadrupole up in ion guide mode, we put a different set of voltages on the rods. And now if we have the same ion beam coming in, containing many different mass-to-charge ratios, all of those ions will pass down the middle of the quadrupole and out the other end. So it's almost like we're using the quadrupole as an ion guide or an ion pipe to move ions around. So if you can change a quadrupole from working as a mass filter to an ion guide simply by changing the voltages you apply to the rods, exactly what voltages are we supplying to these electrodes? Although we have 4 electrodes in a quadrupole, they're actually connected into 2 pairs, the X pair and the Y pair, and we supply one particular voltage to the X rods and a different voltage to the Y rods. In both cases, that voltage has a DC offset and an alternating component that usually has a frequency somewhere in the radio frequency range. In these formulae, U is the DC offset, measured in volts, V is the amplitude of the alternating component, also measured in volts, and omega is the frequency of that alternating component, in radians per second. And lastly, T is time, measured in seconds. The voltage applied to the Y rods is the inverse of the voltage applied to the X rods, like this. So when the voltage on the X rods is high, the voltage on the Y rods is low. And when the voltage on the Y rods is high, the voltage on the X rods is low. On the next slide, we'll look at the electric field generated in the middle of the quadrupole when we apply these voltages to the rods. On this slide, we're mainly looking at the potentials generated in the middle of the quadrupole. That's the bit that the ions would be in. As for the color axis, red indicates high potential, blue indicates low potential, and green is for 0. But it's much easier to view this projection in 3 dimensions instead. So in this case, the vertical axis shows the voltage, and this is the X coordinate along here, and the Y coordinate along here. So at this point of time, the voltage on the X rods is low, and the voltage on the Y rods is high. And if we move forward half a cycle, now the voltage on the X rods is high, and the Y rods is low. So you can see the potential of this surface is constantly changing. First the saddle is one way up, and then it's the other way up, and it flips backwards and forwards as we go through the RF cycle. Now let's imagine we have a positive ion on this surface. This positive ion is going to behave very much like how a ball bearing would behave if this was a real physical surface. So we're starting the ball bearing up here near the highest potential, and it's going to try to roll down towards this valley. But if that valley becomes a hill before the ball bearing reaches the edge of the surface, it'll change direction and now be directed towards this valley. But again, if that valley becomes a hill before the ball bearing reaches the edge of the surface, it'll change direction again and now be headed towards the back valley. So you can imagine how on this surface, if we had the hills and the valleys having the correct heights and depths, and the rate with which they swapped positions being correct, we could keep a ball bearing trapped on this surface indefinitely. And the same is exactly true of how we keep an ion trapped in an electric quadrupolar field. So for an ion trapped in a quadrupolar field, first it's being attracted towards one set of rods, but before it manages to get there, those rods become repulsive and it's attracted by the other pair of rods, and so on indefinitely. But this trapping of the ion will only occur if the voltages and the frequencies with which those voltages change are correct. So how can we predict which combinations of voltages and frequencies will result in an ion being stably trapped in a quadrupolar field? Fortunately, the equations that let us calculate if an ion will be successfully trapped in a quadrupolar field are well known. They're called the Mathieu equations. If you know the ion mass to charge, the voltages, the frequencies, and the size of the quadrupole you want to trap the ion in, then these equations will let you calculate A and Q, the so-called Mathieu parameters. These equations are called the Mathieu equations and the parameters the Mathieu parameters because they were discovered by a French mathematician in the 19th century called Émile Léonard Mathieu. During his career, Mathieu worked on a variety of different areas of mathematical physics, including electrostatics, magnetostatics, electrodynamics, and elasticity. And the particular branch of maths that we're interested in is the work he did looking at the vibrations of elliptical surfaces, like drumskins. Luckily for us, it happens that the same equations he worked out for those also work for the motions of ions in quadrupoles. One other thing to know about Mathieu was, and particularly in view of the horrible maths we're about to go through, is that alongside being a genius, he was also famously nice. After he died, his friends said of him that he was an essentially straightforward, sincere, and generous person and was kindness himself. When he was fatally ill and heading towards his own death, he didn't tell his colleagues how ill he was, because he didn't want them to feel they had to do his examinations for him. And after he died, his colleagues in his faculty said, "His loyal and trustworthy character made him esteemed and beloved by all. In the faculty at Nancy, he had none but friends." So it's important to remember that you can be nice as well as a genius in science. When using the Mathieu equations, it's important to remember that all the parameters have to have SI units. So the potentials applied to the rods, that's U, the DC offset, and V, the peak-to-peak amplitude of the RF component, need to be in volts. The quadrupole radius needs to be in meters, not centimeters or microns. The mass of the ion needs to be in kilograms, not daltons, and definitely not in AMU. The charge on the ion needs to be in coulombs, and the RF frequency needs to be in radians per second. One other thing to note, that the quadrupole radius, that's called R0, is the distance from the center of the quadrupole to the nearest face of a rod. If you look closely at the Mathieu equations, you can see that the equation for both A and Q are inversely proportional to the mass-to-charge ratio, and that's how we can use them in a mass spectrometer. To use these equations, you calculate the A and Q parameters of your ion, and use them as coordinates to plot a point on this diagram, the so-called Mathieu stability diagram. You can see that it has A and Q axes. If the A and Q parameters of the ion cause it to plot in this triangular region, then that predicts that the ion will be trapped within the quadrupole potential field indefinitely. If the ion plots outside this region, then that tells you that the ion will not remain trapped in the potential surface, and will at some point collide with one of the electrodes. But I can't just give you these equations and this stability diagram to use like black boxes, because we don't really like black boxes in analytical chemistry. So the next question is, where do these equations really come from? In order to derive the quadrupole Mathieu equations that I showed you on the last slide, we have to bring two different pieces of information together. So we'll start off with looking how an ion will move or be accelerated in a quadrupole-shaped electric field, and we'll also look at how nonlinear forced oscillators move according to the maths developed by Mathieu, and then we can bring them together to finally derive the equations. We'll start by looking at how an ion moves in a quadrupole-shaped electric field. But before we start, it's a good idea to start thinking about how you can use the slides ahead. We're about to go through a fairly long and quite complicated derivation. The best way for you to understand and follow this derivation will be to repeat it on paper yourself as we go through. Unlike the normal slides in these presentations, the following slides will all stop at the end of the slide and wait for you to go through the derivation by hand yourself, and then you can click the red arrow to move on to the next slide when you're ready. In this way, you'll be able to go through the derivation step by step at your own pace, and it's important you do this so that you can understand how the equations are constructed. If you remember back to your school level physics, for any object that's accelerating, if you know its mass, you can work out the force that must have been applied to it, because the force equals the mass times the acceleration. Another way to write acceleration is the second derivative of position with respect to time. So this part of the equation here just means mass times acceleration. If you need to be reminded about the relationship between position, speed, and acceleration, click this website to find out more. Of course, ions in a quadrupole will have a charge as well as a mass, and we can work out the force that the electric field in the quadrupole can apply to the charge in the ion using this part of the equation, where E is the charge on the ion, and d phi by du means the change in potential by the change in distance, which is of course the electric field gradient. We can calculate the potential that an ion will see at any point within the quadrupole using this relationship here. So phi is the potential the ion will see at a particular x and y coordinate, phi naught is the potential at the rod surface, r naught is the quadrupole radius, and x and y is the position of the ion. To make the derivation easier, let's make the assumption that we're dealing with an ion which plots exactly on the x-axis, so its y coordinate is 0, and we can remove it from the equation. The next step is to calculate the field gradient by differentiating the phi equation with respect to x. If you've not done differentiation in maths before, this would be a good thing to approach the library to get one-on-one maths tuition help with. So if you've managed to go through the derivations on this page by yourself now, then you can click this arrow to move on to the next page. From the previous slide, we have these two equations. This first equation lets us calculate the electric field gradient experienced by any ion on the x-axis, providing we know its position. And this equation lets us calculate the force applied to an ion as a function of its charge and the field gradient that it sees. Because we have this field gradient term in both equations, that means we can combine them together. You have to remember that u can be x, y, or z. So in this case, we're thinking of the electric field gradient in the x direction. So u is x. So we take the right-hand side of the first equation and replace the d phi by du term in the second equation with it, like this. And the other thing you'll notice is that all the little subscript u's have become subscript x because we're dealing with ions moving only in the x direction. And before we leave this slide, I just want to draw your attention to this phi naught term here. So this phi naught refers to the potential difference between the two rod sets, and on the next slide we'll go on to look how to calculate that. We know that the voltages applied to the electrodes in a quadrupole are not constant. They have that radio frequency cosine component within them. So this means that the phi naught term that was in the previous equation will be varying as a function of time. Hopefully you can remember that the voltage being supplied to the x rods is U plus V cos omega t, and the voltage being supplied to the y rods is the inverse of that. And using these two relationships, we can easily explain why phi naught, the total potential difference between the rod sets, equals 2 times U plus V cos omega t. So while the potential being applied to the x rods is U plus V cos omega t, the potential supplied at the same time to the y rods is the inverse of that. So you can see the total potential difference between the x rods and the y rods is 2 U plus V cos omega t. So here again we have the equation from the previous slide. And because the function gets quite long, I'm just going to drop this bit off the front of it because we don't need it anymore. but it still tells us that mass times acceleration for an ion still equals the force generated on its charge by the electric quadrupolar field. And now we can take our time-varying function for phi naught above and substitute it in for the phi naught in this equation. What this tells us is the acceleration of an ion in a quadrupole will not be constant in time. It will vary as the voltage varies on the surface of the rods. This is just the equation copied from the last slide. The next stage in the derivation is to rearrange this equation to solve for acceleration. The d squared x by dt squared term is the acceleration, so to solve for that we just need to divide both sides by mass. And that leaves us with this equation. And the last step in this part of the derivation is to expand out the brackets. So having started looking at the force applied to charged particles in electric fields, we've ended up with an equation that tells us the acceleration of ions, particularly in quadrupolar fields. So that means we've completed the first branch in this diagram. So now we can go on to the second branch. How does a nonlinear forced oscillator move, and how can that be explained using the canonical Mathieu equation? Imagine we built a pendulum with a pivot at the top and a freely swinging bar hanging underneath. Now if we let go of the pendulum, it'll swing backwards and forwards with a regular motion because the only force acting on it is the constant force of gravity. But what happens if we add an extra force? For example, what would happen if we were to also move the pivot up and down at the same time as the pendulum is swinging? What happens to the pendulum then depends on how far you're moving the pivot and how fast you're moving it. This video was created by Harvard University to demonstrate just this point. So in this case they have a pendulum hanging from a pivot, but that pivot is attached to a jigsaw so they can move it up and down very rapidly. With the jigsaw off, the pendulum swings as normal. But when the jigsaw is turned on, the pendulum pivot is moved up and down cyclically, and the frequency and amplitude of that motion is enough to allow the pendulum to swing upside down. If the speed that the pivot was moved wasn't fast enough, or the amplitude wasn't high enough, this stabilization effect wouldn't occur. So we have to choose exactly the right speeds of oscillation and amplitudes in order to get this pendulum to swing upside down stably. This is exactly the kind of situation where Mathieu's equation on forced motion applies, and it also applies for ions in a quadrupole. In a quadrupole, an ion is first attracted, then repelled, then attracted, then repelled by the voltages applied to the quadrupole rods. And just like the inverted pendulum in the video, if we get the amplitudes and frequencies of that voltage change correct, we can keep that ion stably trapped. If we get it wrong, the ion motion won't be stable and the ion will hit one of the rods. Mathieu developed this equation to help handle the situation where you have something that's oscillating, but the force that's causing that oscillation can be varied in both frequency and amplitude. And that's just like our ion in the quadrupole that is being pushed and pulled first in one direction then the other by the cosine waves being applied to the different electrodes in the quadrupole. So the aim of this branch of the derivation is to work on the canonical form of the Mathieu equation until we can derive another equation that also describes how a particle that's undergoing this kind of oscillation must be accelerating. You've probably spotted this horror hiding in the equation above, and it may not be a Greek letter you've come across before, but it's the letter xi. When used in writing, xi would have the same sound that x would have at the end of our word, box. So really we're just using xi like we might use x in an equation. And why isn't a nice simple x being used? Well, it's because we're already considering x as one of the dimensions, x, y, and z, and it would be confusing to have two different x's in the same equation, so we're just using xi to make sure that we know it's different from the normal x. And what is xi? Well, in this case, xi is related to the drive frequency. So you can see the omega here corresponding to the radio frequency that's being applied to the quadrupole rods. So xi equals omega t upon 2, and the first thing we're going to do is differentiate that with respect to time. So that gives us dxi upon dt equals omega upon 2. The other thing we can do with the xi equation is substitute it into the canonical Mathieu equation. So all we do is replace the xi with omega t upon 2, and then the two 2's cancel to give us this result. What follows next looks like a piece of mathematical witchcraft or sleight of hand. If you look at this equation here, you see we have du by dt, that's the change in position, divided by the change in time, effectively that's speed, so du by dt equals dxi by dt times du by dxi. And the dxi's cancel, so really what this equation is telling us is that du by dt equals du by dt. Except that we know what dxi by dt is, that came from the last slide. So dxi by dt equals omega upon 2. So the next step in the derivation is simply to substitute this equation into this one. So that tells us that du by dt equals omega upon 2 by du by dxi. The next thing is simply to rewrite that equation in a different way. The bits that don't include the u's are known as the operators. So the next thing we'll do is we'll square them on both sides, which still lets the equation be an equation, but it gives us a different final result. So let's just remind ourselves about the two equations we've been discussing. Firstly, here is the equation that we got from applying mathematical sleight of hand to the xi equation, and next to it we'll put the canonical Mathieu equation, but with the xi equation substituted into it. If you look here, you can see that both of these equations share a common term. And that means we can combine the two together like this. Now you'll see that this equation is currently in u, whereas we need it specifically in x. So that's the first change we'll make. And the other thing we'll do is just tidy up the right hand side. Make sure you can do this stage of the derivation yourself comfortably. But now this equation calculates acceleration for an object that's undergoing the kind of forced motion predicted by the Mathieu equation. So that means now we've completed the second branch of this derivation. And our next job is to bring these two equations together. So we have our equation for the acceleration of a particle in a quadrupolar field, and an equation for the acceleration of an ion undergoing Mathieu-type motion. And as both of these contain the acceleration term on the same side, we can combine them together into a single equation. So hopefully this is the same equation you'll have got from the previous slide. If not, have another look at your working and just see where you may have gone wrong. And now there are a few things we can tidy up. Both sides are negative, so we can cancel that. And both sides are functions of x, so we can cancel that. And finally, there's some integer terms that we can also tidy up. And if we do each of those three steps, this is the resulting equation. There's a few further steps we can do to tidy up this equation some more. You see these m r0 squared terms on the left hand side? Well, we can move them across to the right hand side, and then we can multiply out the brackets to give us this equation. The next stage is to move all the cosine containing components to one side of the equation and all the non-cosine parts to the other. And so that gives us this equation. The next step is to simplify the right hand side, because both parts of that have a cos omega t and both are multiples of even numbers. The next step in this derivation relies on the fact that the right hand side of this equation is a function of cos omega t. And if you remember, a cosine wave is 0 twice every period. And when cos omega t is 0, the whole right hand side of this equation is 0, like this. And now, having got here, we can simply solve for a. And now, if we go back to this equation again, we can treat it in a slightly different way. If we were to set u, that's the DC offset, to 0, then as we've just seen on the previous slide, that would also mean that a equals 0. And then, the whole left-hand side of this equation becomes 0. Then, because 0 divided by any number is still 0, that means we can get rid of this part too. Which means we're just left with this. And then the last step is to solve that for q. And that completes the derivation. So we started off with looking how an ion moves in a quadrupole-shaped electric field, and how a nonlinear forced oscillator moves, and combining those two equations together, we derive the quadrupole Mathieu equations. Make sure you've gone carefully through each step in the derivation so you can understand what happened. And of course, if you find any errors that I've let creep in there, please tell me. So now I've explained where the quadrupole Mathieu equations come from, let's have a look at the stability diagram. I've labelled the diagram to show what happens to stable ions. So in the central triangle they're stable in both directions, in other places they're stable only in the x direction, or stable only in the y direction, or unstable in both. But what exactly happens to the unstable ions? Stability in this context doesn't refer to the lifetime of the ion and whether or not it spontaneously breaks up. Instead, stability refers to the trajectory. So for an ion whose AQ coordinates put it in the stable region, that means that its trajectory remains within the bounds of the quadrupole as it travels along the length. So for the case of this red ion, that might look something like this. For ions that plot outside the stable region, that means the ion's trajectory will eventually cause it to hit one of the rods. But how it does that will depend which side of the triangle it's on. For ions like this one out the left-hand side of the triangle, their amplitude of oscillation stays about the same, but their average displacement increases until the ion hits a rod. For ions like this one that plot out the right-hand side of the stability diagram, their average displacement stays at 0, but now the amplitude of their oscillation will increase until the ion hits a rod. In a later session, we'll look at why these ions behave in different ways. But for now, let's try to understand how we can use a quadrupole to act as a mass filter. Let's imagine we have a mixed beam of ions of different masses travelling along the length of a quadrupole. For those ions, if we set the quadrupole up with a DC offset and an RF amplitude, the ions will plot on a line because both A and Q are inversely proportional to the mass to charge ratio. But if we do that, where will the heaviest ions end up? Will they be towards the A end of the line or towards the B end of the line? The line that ions plot on in the Mathieu stability diagram is called the scan line. And the gradient of the scan line, like for any straight line on a graph, is defined by dy by dx. But in the case of the stability diagram, the axes are q for the x-axis and a for the y-axis, so the gradient of the scan line can be described as dA by dq. Because a is proportional to u, that's the DC offset, and q is proportional to v, that's the RF amplitude, that means that dA by dQ is proportional to the U to V ratio. And on some older quadrupole or even ion trap instruments, you may actually have a U to V control available to you in the software. But when running a quadrupole as a mass filter, the U to V ratio is set so that the scan line just passes through the tip of the stability diagram like this. And it's set up like this so that only a tiny region of the available mass to charge ratio space will be stable at any given time in a quadrupole, and only ions of that specific mass to charge ratio will make it all the way through the quadrupole and hit the detector at the far end. All the other ions that exist in the quadrupole at that time will have unstable trajectories and will hit the rods and so will not be detected. So how can we use this information to collect a mass spectrum? Let's imagine that the ion beam trying to pass down the length of the quadrupole contains 4 different ions, each with different mass to charge ratios. All of these ions will plot on the scan line, with the heaviest ion nearest the origin. Now, once the ions are in the quadrupole, we undertake a process known as scanning the RF. This means we're going to increase both the DC offset and the RF amplitude at the same time, but keep the ratio between them constant. So during the RF scan, the voltages will go from low to high. And so the corresponding voltages being sent to the quadrupole rods look like this. For both the X and the Y rods, the voltage amplitude and DC offset increase linearly during the length of the scan. So if we go back to this view now, here are our ions on the scan line at the beginning of the ramp. Now, as we scan the RF, because the A value for every ion is proportional to U, the DC offset, and the Q value for every ion is proportional to V, the RF amplitude, as we increase these together, ions appear to slide up the scan line. So now let's look at that again, but this time think about what signal will be seen on a detector at the far end of the quadrupole. At the beginning of the ramp, all the ions are outside the stable region, so there'll be no ions hitting the detector. Then, as we increase the ramp, one after the other, the ions pass through the stable region at the tip of the diagram, and so we'll end up getting 4 distinct peaks on the detector at different times during the ramp. So in order to convert this time-based spectrum to a mass spectrum, we have to collect a similar spectrum of ions of known mass using the same RF ramp, and then we can apply the mass calibration coefficients from that spectrum to this one. But before we leave this slide, let's just have another look at the ions moving up the scan line and resulting in the 4 peaks in the spectrum. A different way to use a quadrupole mass filter is to keep the U to V ratio constant and not ramp the RF at all, but fix it so that one ion only remains in the stable region and all other ions passing through the quadrupole are unstable. And in that way you can set up a quadrupole mass filter to look at the intensity of just one ion for a very long period of time. And as we'll see later in the course, this is very useful for methods such as tandem mass spectrometry. But what if you left the DC potential off? That is, if you set U to 0. Where would the ions line up then? Click on the stability diagram to show where you think the ions would line up if U equals 0. So if U is 0, then A equals 0 for all ions. And that means that the ions just line up on the Q axis. And now you can see that unlike before, all of our ions of different mass to charge ratios are in the stable region at the same time. So quadrupoles with no DC offset, that's RF only quadrupoles, can be used like pipes to move ions around inside an instrument. They don't offer any mass selection, but they're still a very useful way of allowing you to move ions around. So to return back to this slide that we saw all the way back at the beginning of this presentation, quadrupoles have two main modes of operation. There's mass selective or mass filter mode, and that's when you're supplying both an RF and a DC offset to the quadrupole. And there's ion guide or RF only mode, when there's no DC offset, so all the ions line up on the Q axis. And finally, if we go all the way back to this slide, the very first one in this presentation, you can see that if you look at the quadrupoles, some of them are labelled with a capital Q and some of them with a lowercase q. The quadrupoles labelled with a capital Q are those capable of mass filtering, so they have both an RF amplitude and a DC offset. And the quadrupoles labelled with a lowercase q are for ion guides only. They have no DC offset. There's quite a lot of information in this presentation, but if you want to look for more information to help you understand it, there's some really good simple guides on quadrupole theory provided by Ardara Tech, and I've given the link on the slide here. Otherwise, navigate to www.ardaratech.com, go to the document library, and then technical notes. And these have been written by a friend of mine, Randy Pedder, who runs Ardara Technologies, and has been working on quadrupoles since dinosaurs were eating other dinosaurs. Sorry, Randy. As we did with time of flight mass analyzers, let's look at some of the constraints and capabilities of quadrupole mass analyzers. Firstly, the pressure. You need quite a good vacuum in quadrupole mass filters, because we need the ion to traverse down the full length of the quadrupole. If the vacuum pressure isn't good enough, the ions will be bumping into background gas molecules as they go, gradually slowing down, and eventually they'll stop and never reach the detector. We don't care exactly how long it takes an ion to go down a quadrupole. We're not measuring their time of flight as in a TOF detector, so it doesn't matter if they have a few collisions, but they mustn't have so many that they stop. So you still need quite a good vacuum in quadrupole mass filters, but just not quite as good as you need in a time of flight. So something like 10 to the minus 5 to 10 to the minus 6 millibars. Speed-wise though, quadrupoles are quite slow. It's rare to be able to collect more than 10 to 20 mass spectra per second. The reason for this is, remember, to record a mass spectrum we've got to ramp the RF. For most of that RF ramp, the ion of interest isn't in the stable region of the quadrupole. Then, even when it is in the stable region of the quadrupole, if we change the voltages too quickly, the ion will enter the quadrupole when it's in the stable region, but will go unstable before it has a chance to get out the back end of the quadrupole, in which case we'll see no signal for any ion at all. So we've got to ramp the quadrupole quite slowly so that ions have time to traverse the full length of the quadrupole while they're still in the stable region. Regarding resolving power, quadrupoles are limited to relatively low resolving power, usually in the range of a few thousand. The reason for this is, it's actually very hard to produce quadrupoles with sufficient mechanical accuracy so as not to perturb the electric fields inside them. Similarly, it's difficult to design and build electronics capable of reliably producing the potentials to supply to the rods as well. So in practice, a quadrupole mass analyzer will never be able to reach the same resolving powers as a time-of-flight instrument. Quadrupoles are also relatively limited in their mass range, usually up to a mass-to-charge ratio of about 15,000. The reason for this is that the tip of the stability diagram is at a fixed value of A and Q, but both A and Q are proportional to the voltages, but inversely proportional to the mass. So as you want to get the mass higher and higher, you also have to be capable of producing higher and higher voltages. And eventually you get up to a voltage so high that it simply arcs between the rods, and that gives you a hard limit on the mass range you can produce through that quadrupole. To increase the mass range available to quadrupoles, the usual approach is to reduce the frequency. You see that's on the bottom of the fractions for both A and Q. So as you reduce the frequency, that allows you to also reduce the voltage. And this is the strategy used by most companies who offer extended mass range quadrupoles. Now, looking at the other capabilities, a single quadrupole mass analyzer isn't capable of tandem mass spectrometry, because although it can select an ion, it can't fragment it and then create a mass spectrum of the fragments of that ion. But I'll show you later how to build a tandem mass spectrometer that is built of quadrupoles. The sensitivity of quadrupoles tends to be pretty good. Firstly, they use the same kind of multiplying detectors that time-of-flight mass analyzers used, but also you'll remember they have that capability of fixing the ion they look at to just a single mass for a long period of time, and that allows you to get extremely good sensitivity for that mass. Cost-wise, single quadrupole mass spectrometers tend to be the lowest cost mass specs out there. And the reason for that is, although it's difficult to build the RF electronics, once you've worked out how to design them, the components in them are relatively cheap, unlike the extremely fast electronics and high voltage electronics needed to run time-of-flight instruments. And complexity-wise, they're pretty simple. But the instruments are complicated by the fact that because the mass spectral performance isn't very high, they don't have very good resolving power or mass accuracy, they're nearly always used with some kind of chromatography, and that increases the complexity of the overall system. But despite their modest performance, once coupled with chromatography, single quad mass specs are the workhorse of many analytical labs. They provide the detection end of most GCMS systems and nearly all LCMS systems in basic use. So if you go on to work in the field of biomedical research or pharmaceutical development, you'll almost certainly be using single quad mass specs. Now in this presentation, we've gone through the derivation for the Mathieu equations for quadrupoles. The Mathieu equations for ion traps are slightly different. So before the next session, I want you to go through Ray March's tutorial on the introduction to ion traps and write out in your own words the derivation of the equations from 2 to 24. Those of you who are watching this tutorial from inside NTU will find Ray March's paper in the electronic workspace. Or if you're watching the HTML5 version of this presentation, just click on the paper below. Finally, if all else fails, go to Google and type in Ray March quadrupole tutorial and up it'll come. Again, if you're an NTU student and you get stuck in this derivation, come and ask for help before the session. I've also made an HTML5 version of this video. The benefit of watching the presentation in HTML5 mode is that you get to go through it at your own pace and answer questions and problems as you go along to help you understand the material. To find the HTML5 versions, go to the Kilgour Lab website at www.kilgourlab.com and then go to the Teaching Resources page. On there you'll find a whole variety of resources to help you learn about mass spectrometry. I hope you enjoy them. And so that brings us to the end of this first lecture on quadrupoles.